Hi, my name is Udit and I'm a sixth-year PhD student at Harvard University, and today I'm going to be sharing our work called RecPipe. In this work, we demonstrate the importance of co-designing models and hardware to jointly optimize end-to-end recommendation engines for both quality and for performance. Now, personalized recommendation engines are used to recommend content on internet services that we're using on a daily basis. This includes YouTube, search, social media platforms, and e-commerce platforms. Now, our previous work demonstrates that recommendation systems consume a significant portion and even the majority of AI infrastructure capacity within production data centers. We also find that they pose unique performance bottlenecks. Now, because of this, we have seen proposals to accelerate recommendation engines with specialized hardware. So here on the left, we see the generalized network architecture for recommendation models. Models implement compute-intensive DNN layers, memory-dominated embedding operations, and communication-dominated feature interaction layers. Recent proposals to accelerate recommendation target each of these different bottlenecks. For DNN layers, accelerators implement gem-like units like systolic arrays, and for embeddings, accelerators implement an embedding gather unit and embedding cache in order to house frequently accessed vectors. We find that accelerating these key operations yields a very impressive 6 times performance improvement on individual recommendation inferences. However, we also find that these accelerators suffer from low efficiency on end-to-end recommendation services that implement multiple stages. To understand why, let's take a look at an example of a production service. These services implement multi-stage recommendation engines. Here on the left, we see candidate items that are taken as input and first evaluated and scored with lightweight neural network models in order to perform coarse-grained filtering and produce a smaller subset of relevant items for individual users. This reduced subset of items is then ranked with heavyweight models in order to produce a few items to recommend to users. These type of recommendation pipelines are crucial for production services in order to serve billions of users worldwide with high quality and high efficiency. Intuitively, across this multi-stage pipeline, going from left to right, we see increasing model complexity. This means that the model compute intensity, storage capacity, and network accuracy are improving as we go down across the stages. Going from left to right, we also see that the number of items ranked is going down. Now, because production recommendation services use these types of multi-stage pipelines, hardware accelerators face many limitations because they are designed to accelerate individual models. Let's take a look at some of these limitations. First, across each pipeline stage, we find varying performance bottlenecks. Front-end models have high data level parallelism that we see on the left, while back-end models have high model level parallelism. Specialized ASICs suffer from low utilization when accelerating workloads with varying performance characteristics. Next, in addition to the inferences, each stage has to perform top K filtering operations and sorting operations. Now, as accelerators speed up model inferences, these top K filtering operations can actually limit end-to-end performance speedup. And finally, we find that across different production recommendation services, each service has different application level targets in terms of tail latency, throughput, and recommendation quality. Hardware accelerators have to be designed in order to flexibly optimize these varying performance targets. To address these limitations, this work proposes very deep model hardware co-design for end-to-end recommendation pipelines. Before we get into the core results and the design contributions of this work, let's see the performance optimization opportunity available by co-designing models and hardware. So here on the y-axis, we have latency, and on the x-axis, we start with a baseline one-stage CPU recommendation engine, and we'll add model-only optimizations, hardware-only optimizations, and model and hardware optimizations. Starting with model-only optimizations, we find the performance on commodity hardware systems such as CPUs and GPUs improves by about 2x. On the other hand, hardware-only optimizations by designing specialized hardware improves performance by a very impressive 6x. Now, in this work, we find that co-designing across models and hardware accelerators improves performance by a further 3 times on top of the very aggressive accelerator baselines. Now, to recap, in this work, the key challenge that we're trying to address is how can we design hardware to co-optimize quality, tail latency, and throughput across end-to-end recommendation pipelines. First, we're going to understand and look at the available model hardware design space that we can optimize over. Next, we're going to characterize the performance of recommendation pipelines on commodity hardware platforms. And with the intuition that we gain from this characterization, we are then going to design specialized hardware for end-to-end ranking. Now, with this specialized accelerator called RPAccel, then we're going to look at the end-to-end performance analysis of the proposed hardware design. First, let's take a look at the model hardware design space that's available. To study this design space, we designed the RecPipe infrastructure that's shown here. In the middle, we see the multi-stage recommendation workload, where each stage implements a pre-trained neural recommendation model in order to score items. Finally, at the right, we output the top K items to the user. At the output, we also measure metrics such as the tail latency, the quality, and the overall system throughput. Now, in the paper, we explore trade-offs across all three optimization axes, but for the purposes of this talk, we're going to be focusing on ISO quality results. To explore the trade-offs that RecPipe offers, here we highlight the design space that RecPipe allows us to optimize over. In red, we're seeing the model design space, including the number of stages, the items to rank per stage, and the model size per stage. In addition to these modeling parameters, we implement the RecPipe inference scheduler. Now, this scheduler maps each stage of the recommendation pipeline onto available hardware platforms. This includes commodity CPU and GPU platforms, as well as the specialized accelerator that we're going to be designing throughout this talk. Now, before we go into the empirical characterization over the model in the hardware design space, I first want to call attention to the way that we measure output quality. In fact, we find optimizing for recommendation quality is not the same as optimizing for network accuracy. We find optimizing for quality actually enables the algorithm level and the model level design space that RecPipe optimizes over. So on the left here, we're seeing test error on the y-axis and model complexity on the x-axis. As expected, as we go from left to right and increase in model complexity in terms of 8 times by size and 16x in terms of compute intensity, we see the test error also go down. On the right, we use a metric called normalized discounted cumulative gain, or NDCG, to quantify quality. As we increase the number of items ranked, the quality of the items recommended also improves. Intuitively, this is because increasing the number of items ranked also increases the likelihood of finding good user item matches. On top of the number of items ranked, we find increasing model complexity also improves overall recommendation quality. Now, this analysis shows that while optimizing for accuracy depends solely on maximizing model complexity, optimizing for end-to-end recommendation quality actually depends on both model complexity as well as the number of items ranked. So next, we're going to be looking at characterizing these multi-stage recommendation pipelines across commodity hardware platforms. So here we're highlighting the model in the hardware co-design space that we're going to be considering for the next portion of this talk. So starting with commodity CPU platforms, here on the x-axis, we see system throughput, and on the y-axis, we see tail latency. And the black line illustrates the performance of a single-stage CPU baseline. Going from the one-stage design to the two-stage design, we reduce tail latency by up to 4x. Now, in the paper, we show the impact of model complexity across stages on the overall quality and the performance. We can also further decompose the pipeline into 3 stages. But unfortunately, we find that the additional queuing delays across the stages overshadow the benefits of the multi-stage decomposition. Overall, here we're seeing that optimizing the modeling parameters across end-to-end recommendation pipelines enables higher performance at ISO quality. Now, in addition to general purpose CPUs, there's been a lot of interest in using AI accelerators in order to improve the efficiency of AI at the data center scale. One example of this AI accelerator is a GPU. For the next portion of this talk, what we're interested in thinking about is how can we most efficiently use both general purpose CPUs and GPUs to efficiently perform end-to-end ranking across multi-stage pipelines. And central to this discussion is going to be the fundamental hardware differences across CPUs and GPUs. So CPUs have high task level parallelism with a many core architecture and large DRAM capacities, whereas GPUs are going to have high data level parallelism with limited DRAM capacity. So here we're looking at the performance trade-offs of scheduling multi-stage recommendation pipelines on CPU and GPU platforms. So once again, on the x-axis, we have system throughput and tail latency on the y-axis. And in red in the middle over here, we're seeing the optimal two-stage CPU design that we saw earlier in this presentation. In black, we're seeing the single-stage GPU-only design. And we find that this GPU-only design has 3 times lower tail latency. Intuitively, this is because GPUs accelerate batched inferences. However, this GPU-only design also suffers from 2 main drawbacks. The first is that at high system loads, the GPU-only design has poor tail latency. This is because the GPU-based design suffers from low task level parallelism. The second drawback is that GPUs have limited DRAM capacity, which makes running larger models quite challenging. To address these drawbacks, we can actually schedule the multi-stage recommendation engines using a 2-stage approach. The first stage runs on the GPU to exploit its highly data parallel architecture, and the second stage runs on the CPU in order to exploit the larger DRAM capacity. Unfortunately, we still find that this 2-stage GPU-based design has lower performance than the CPU-only design that we saw earlier. This is due to low compute utilization and high PCI communication overheads between stages across the CPU and the GPU-based platforms. Now, generally what we've seen through the characterization is that hardware-aware model designs can yield very significant performance wins. However, on commodity hardware platforms, we are still seeing low GPU efficiency from underutilizing the compute units and having high PCIe overheads. Now, given these limitations, our next step is going to be to design specialized accelerators, RPAccel in this case, in order to speed up end-to-end ranking. So here is the design space that we're going to be optimizing over in the next portion of this talk. And to get some intuition on how we designed the proposed hardware accelerator, we're going to first start with the baseline single-stage accelerator. And here we're looking at the workload. So we take input items, we rank them with a large neural network. After the neural network produces predicted click-through rates, we are then going to take those scores, perform a filtering and a sorting operation in order to output the top few recommendations that are then served to the user. The hardware view of this is shown below over here, where in gray we have the accelerator that implements a monolithic systolic array in red and a static embedding cache to house frequently accessed vectors in blue. And the filtering operation is running on the host CPU, and that's step 2 that you're seeing over here. So to design the proposed hardware accelerator, the first step is the model level optimizations that we've been talking about. So here we're looking at the model level optimizations, which reduce the overall algorithmic complexity by taking the single stage large neural network and splitting it up into a front end stage, which has a smaller neural network, and a back end stage with a larger neural network. After each of the stages in yellow, we're seeing that we have to perform this top K filtering operation. Now, the hardware view of this is relatively straightforward. First, we run the small neural network inference on the accelerator, the filtering operation on the host CPU. We send the outputs back to the accelerator, and we perform the larger neural network inference on the accelerator. And finally, we perform the top K filtering operation on the host CPU once again. Now, you can see how this design is going to incur a lot of PCI communication overheads and potentially limit the performance of this hardware accelerator. So next, let's look at the hardware specialization that we can add in order to accelerate these end-to-end recommendation pipelines. So we're going to start with 2 optimizations. The first is targeting the ability of the accelerator to run concurrent models and queries at the same time in order to improve throughput. The way that we're going to do this is we're going to take that monolithic systolic array in red and split it up into multiple subarrays that can operate independently. The second optimization is going to be to eliminate the PCIe overhead from the top K filtering operation by actually performing the operation on chip on the accelerator. And you see that highlighted as the yellow portion within the accelerator itself. The next optimization in order to reduce average memory access time is to provision resources in the embedding cache for both the front end and the back end model so that we can reduce overall memory access times. And finally, instead of performing the inferences as a single batch, we're actually going to perform them in multiple batches. And what this is going to allow us to do is actually pipeline the batches and overlap the front end and the back end stages in order to reduce overall tail latency once again. Okay, so let's take a look at what the performance potential of each of these different optimizations is. Here, we're going to be conducting an ablation study, starting with the single stage accelerator baseline that we looked at. And first, applying the model level optimizations, going from a single stage to a multi-stage recommendation pipeline, we see that that improves tail latency by 2.5x. Now, next we can look at the hardware level optimization. So first we look at adding the filtering operation on chip on the accelerator. That reduces the latency by 1.5x. The reconfigurable systolic array improves throughput by 2x. And then the embedding caching and the pipelining optimizations further reduce latency by 1.3x. Overall, this provides us a performance improvement of 5 times in terms of latency and 10 times in terms of throughput. Now, next, I want to take a bit of a deeper dive on some of these individual hardware optimizations and take a look at how they're providing these impressive performance wins. So first, we're going to start with the space configurable systolic array. And to gain intuition, we look at the performance and the utilization of systolic arrays across 3 recommendation models: small, medium, and large. And on the x-axis on the bottom, we're seeing varying sizes of systolic arrays. And on top, the y-axis shows cycles or performance, and on bottom, we see utilization of the systolic array. We find that as we increase the size of systolic arrays, we have higher performance, but much lower utilization. And this low utilization means that we have unused hardware resources that are actually lowering our achievable system throughput. As we look at the larger recommendation models, however, they have higher utilization of the same systolic arrays that we were looking at before. Now, intuitively, this means that we're going to want to pair the larger systolic arrays with the larger recommendation models and the smaller systolic arrays with the small models in order to maximize system utilization. When we do this, we see that starting with a fixed array, the monolithic array from the baseline, which had a utilization of 30%, this reconfigurable systolic array can increase utilization up to 60%, effectively doubling our overall throughput. Now, next, I want to look at the top K filtering unit. So at the top here, we see an example of the top K filtering operation, where the filtering unit in yellow takes as input the predicted click-through rate scores and outputs the top 3 items in red. Each systolic array subunit implements a separate and distinct sorting and filtering unit in yellow over here. And because the output layer of these recommendation models is of size 1, the systolic array produces a single click-through rate per cycle. Taking the streaming click-through rate as an input, each cycle, the filtering unit maintains a running histogram of the output scores. Simultaneously, for the scores that go above a specific threshold, in this case 0.5, we store the ID and the score of the corresponding item within a buffer that is co-located with the weights memory. Once we've produced all the click-through rates, the hardware computes the click-through rate threshold for the top K items. In this case, we set K as 512. And looking at the histogram, the hardware computes that the top 512 items are found in the top 2 bins highlighted in red over here. This means that we have a minimum click-through rate score of about 0.8. And using the score, we traverse the buffer and gather the item IDs for the corresponding top 2 bins. Now, performing this top K filtering operation on chip actually eliminates the PCI communication overheads, yielding this 1.5x speedup that we have seen earlier. Now, this performance improvement is at negligible area and power overheads. Now, in the interest of time, we won't be able to go through all the other design features within the proposed hardware accelerator. But if you're interested, I encourage you to take a deeper look at our paper. But I want to conclude this talk by looking at the end-to-end performance analysis for RPAccel. So here on the x-axis, we see system throughput, and on the y-axis, once again, we're looking at tail latency. And the gray line is the baseline recommendation accelerator, and the black line is a one-stage RPAccel accelerator. Now here we're adding the two-stage accelerator design in red and the three-stage accelerator design in blue. And what we find is that by doing this deep model hardware co-design across the multi-stage recommendation baselines, we can improve throughput by nearly 6 times at ISO quality and ISO latency, or improve tail latency by 3 times at ISO quality and ISO throughput. Now, additional details on how the accelerator is reconfigured for these different performance targets can be found in the paper. But generally, what we find is that these impressive performance improvements come at a low area penalty of about 7% and a low power penalty of about 27%. And this is based on synthesizing the hardware components in a GlobalFoundries 12 nanometer process technology node. Now, to recap, what we've seen in this talk is the importance of co-designing across the model and hardware accelerator designs, and doing so yields very impressive 3 times latency and 6 times throughput wins over aggressive accelerator baselines. Now, if you're interested in this work, I definitely encourage you to take a look at our paper. We have a lot more details on the different design trade-offs and the evaluation results. We've also open sourced the RecPipe infrastructure, and you can find it on GitHub. We've also gone through the artifact evaluation process and received the artifact available, functional, and reproducible badges. And finally, if you have any questions, I would be happy to answer any questions that you might have. And thank you for attending this talk.